Welcome. In this video, I wanted to reiterate the things I've said before about projecting vectors onto other vectors, as opposed to projecting vectors against some coordinate system, usually x and y. This time around, in the previous example, we were projecting vector v onto vector p. Now I would like to flip things around, switch the tables, and project vector p bar onto vector v. And remember, two ingredients are important for us to be able to perform this projection. We need to have an angle between the two vectors, and we need to form a right angle triangle in a specific way. The vector which we are projecting needs to be the hypotenuse of a right angle triangle, and that right angle triangle needs to enclose the angle which we have. So over here, we have angle theta, and we have our vector p. It is this vector which we seek to project against vector v bar. So let's go ahead and form a right angle triangle such that vector p is the hypotenuse, and that triangle encloses this angle which we have. So we will drop a perpendicular from the tip of vector p. That's the only way it could be the hypotenuse of this triangle. So here is our right angle triangle. Slightly, it's upside down, but something we can work with. So now, this vector, this triangle will have two sides. One side is going to be in the direction of vector v, and the other side will be in the direction perpendicular to vector v. And we're going to label those sides appropriately. The first side we're going to start off with is the one that is in the direction of vector v. That's that side. Let's call this the part of p that's parallel to vector v bar. And the other side is this one, the dotted side, which we will label as the part of p that's perpendicular. That's perpendicular. The part of p that's perpendicular to vector v bar. Now, how do we obtain these sides? Well, this side is adjacent to our angle, which, remember, it's the angle which we have. And so this side will be the adjacent side of this right angle triangle, and this side is going to be the opposite side because it's opposite to the angle. The appropriate trig ratios that would enable us to find these are cosine and sine, respectively. So this means, I'm going to skip a couple of steps. This means P parallel V bar is going to be the magnitude, which is in this case P bar, the magnitude, or the hypotenuse rather, which hypotenuse is going to be the magnitude of vector P times cosine of theta. So this is how we would obtain the part of P that's parallel to vector V. And by the same argument, the part of p that's perpendicular to vector v can be obtained using the sine function. Now, as I've mentioned before, if we know the angle explicitly between these two vectors, we could simply plug in the values here. Typically, though, we don't know this angle. Especially in higher dimensions, it's typically difficult to find the angle between two vectors. But we have learned two ways of multiplying vectors, which gives us a way to perform this calculation. And that is the dot product and the cross product. By using the dot product, we will be able to find this component. And by using the cross product, we'll be able to find this component, because the cross product has a sine theta built into it, and the dot product has the cosine of theta built into it. So let's write down the expression of the dot product between vector v and vector p. That is going to look something like this: v bar dot p bar. This is going to be v times p bar times cosine of theta. And as I've said before, that we have given this thing here a name. This thing has a name, and its name is P parallel V bar. So we can rewrite this as V P parallel V bar. So if we want to isolate V parallel P bar in this equation, we simply divide by V bar. So therefore, P parallel V bar is simply going to be equal to the dot product of these two vectors, V and P, divided by the magnitude of vector V bar. Notice what comes in the denominator here is always the magnitude of the vector onto which we're projecting. So here we're taking vector P and we're projecting it onto V. Notice V is in the denominator. In the previous example, we were taking vector V and projecting it onto vector P, and notice what was on the denominator. Or maybe let's go one back. Notice what was on the denominator. It was vector P. We were projecting vector V onto vector P, and notice what makes it into the denominator. And we could argue the same for the component of V that's perpendicular to, the component of vector P that's perpendicular to vector V. That we can use the cross product for. That is, if we had the cross product of V bar times P, and I should say the magnitude of the cross product, that's given by V magnitude of P times sine theta. And again, this thing here has a name. We have given it a name, and its name is P perpendicular V bar. So we can substitute that and say this is going to be, I'm sorry, that should not be a P, that should be a V. That's V bar. There should be P perpendicular to V bar. And by dividing by this V bar here, the magnitude of V bar, we obtain what this P, therefore, P perpendicular to V bar, this is going to be the magnitude of V cross P bar divided by V bar itself. And again, notice the direction onto which we are projecting, or the vector against which we are projecting, always makes it in the numerator. So this is the essence of projecting vectors into other vectors. We use the dot product and the cross product because we don't have a set coordinate system. Actually, when we use the set coordinate system, essentially we are doing the same thing. We are actually doing the same thing. Bear with me, let me argue this out. So, what are you doing when you're finding the x component of a vector? Actually, in the background, you are projecting, maybe before I go there, we know that we have vectors called unit vectors. The unit vector in the x direction is called I hat, and the unit vector in the j direction is called, okay, that doesn't show up as well, it's called j hat. So if I had a vector like this, let's call it v bar, and I had an angle between them, call it alpha. When you're finding the x component, actually what you are doing is you are finding the part of v that's parallel to vector I hat. This is the x component. This is the same as vx. Let's go ahead and find, let's use this formula. I'm going to copy it over here. Let's use this formula over here and try to see what does this give us for our situation. So I'm going to copy this. Maybe let's just simply adapt it. So the part of v that's parallel to vector I hat is going to be v dot I hat divided by the magnitude of I hat. I'm simply just applying this expression here for this situation here. So, in essence, remember vector v can always be written as v sub x I hat plus v sub y j hat. So what is the dot product between v bar and I hat? the dot product between v bar and I hat is going to be Vx times 1 plus Vy times 0, which will give us V sub x. Maybe let me delete that for now. So this is what the numerator, this is what goes in the numerator. Now what about the denominator? The denominator, by definition, this thing here is a unit vector. So its magnitude is 1. So the magnitude of I hat is 1. This means if we substitute these things, Vx in the numerator and the 1 on the denominator, this means the part of V that's parallel to vector I is Vx. Actually, every time you are finding the x component and the y component, you are simply using the same formula, except you are projecting it onto something that's trivial. So that's why you never see what the denominator. So the point is, the idea of projection has always been there. What we have done here and here, we have generalized it, where we are not projecting onto some coordinate system, but we are projecting one vector onto another. So to avoid being too long, I will stop here, and any questions you are always welcome to ask. Okay, see you in the next video.